Okay. Welcome everyone to another session of the data learning seminars. Today we have Dr. Bingqing Cheng from the Institute of Science and Technology in Austria. She did her PhD and EPFL and her postdoc in Cambridge. I'll leave the audience with you, Bingqing. Thank you so much for doing this talk.
Thanks very much for hosting me. So today I'm going to talk about how do we predict material properties with a little bit of help from machine learning. And this work is from with a lot of help from my collaborators with this very long and probably even non-exhaustive list. Now, I would like to start with the big picture. So what is the biggest question? What is the biggest problem that we are trying to tackle when it comes to computational physics or computational chemistry? Actually, the answer was already given by Paul Dirac almost 100 years ago. So Paul Dirac said the fundamental laws that are necessary for us to understand and to model our systems are almost completely known. So namely, he was actually referring to the Schrodinger equation back then. But the problem is that solving these equations are just too complicated and too computationally expensive. So what is the solution? Again, according to Dirac, the solution is to develop approximate methods so that we can solve those equations with trackable time. So with that in mind, let's look at what do we have in our arsenal. So when it comes to computational chemistry, we have a list of methods, and I'm just ordering them on two axes based on the cost and accuracy. So with the most accurate methods, we have quantum Monte Carlo and couple cluster, and we are able to, but with these very expensive methods, we are only able to tackle a system of about tens of atoms. And the workhorse of the field is the so-called density functional theory. But even with that, we can only simulate systems of hundreds of atoms on a time scale of 10 to the minus 12 seconds. And now the take-home message here is that there's a very sharp trade-off between cost and accuracy. And the issue doesn't just stop there, because it's not just the energy of the system that we care about. The entropy also play a significant role. So here in Vienna, we have the grave of Boltzmann, the founding father of statistical mechanics. So on his tombstone, here's the written, they have the Boltzmann, so-called the Boltzmann's equation. And the Boltzmann's equation reads S, the entropy S is equal to the Boltzmann's constant K times the logarithm of the number of microstates. And a microstate is a specific realization of the coordinates and velocities of all the atoms in our system. Now, and actually, this Boltzmann's equation is unfortunately not completely right. In its correct form, we not only have to consider the number of total number of microstates, but also we have to weigh these microstates properly using the Boltzmann's equation. And the microstate is a specific realization of our system. It contains a highly, you can think of it as a high dimensional vector in space. It contains all the information about all the coordinates of velocities of all the atoms in our system. So in order to have a good estimate of the entropy, we need to sample exhaustively all the relevant microstates. That, of course, also imposes a tremendous computational challenge. So this is where the so-called machine learning potential come into rescue. So as I mentioned before, there's in general a trade-off between the cost and accuracy when we model atomistic system, but the machine learning sits in this magic spot that it combines high accuracy with relatively low computational cost. To put these into numbers, so compare with density functional theory, which by the way makes up about 1/6 all the computational usage at supercomputing centers. We are able to tackle like orders of magnitude larger systems with a favorable linear scaling compared with the cubic scaling of density functional theory. We can even run such calculations on our laptops. So how does it work? So instead of treating the machine learning potential like a black box, I would like to provide a view that is more, I would say more atomistic. So if I invite you to look at these two atomic configurations shown on my screen, what would you see? So you might be thinking, okay, the configuration on the right looks like a solid, and the configuration on the left looks like liquid. And the reason why you might be think that way is because all the atomic environments in the configurations on the right are very, very similar. Meaning that if I sit on an atom and I look around me and I look at my neighboring atoms, all these each environment are very, very similar. And in this case, it's a face-centered cubic. However, if we look very, very closely, we can also find very similar atomic environments inside liquid as well. We can even find solid-like environments in the liquid, and I shall come back to this point a little bit later. This is, of course, very hard to see with naked eye. So in reality, what people do is that for each environment, the community has developed many so-called representations. So meaning that we can translate each of these atomic environments into a list of vectors, into a mathematical representation, so we can compare them in an easy and rigorous manner. Now, what does it mean to encounter similar atomic environments over and over again in our simulations? This actually means that ab initio quantum mechanical calculations is quite wasteful. The reason is that we will encounter similar atomic environments over and over again in our simulations. So instead of recomputing them each time, and because the energy and forces of the central atom is almost completely determined by this atomic environment, we can adopt the Turnitin strategy. So each time we encounter atomic environment, we just remember what it looks like and what is the energy and forces associated with this environment. So next time when a new environment comes in, instead of recomputing the energy and forces using quantum mechanical methods, I can just compare the new environment with the ones in my memory so that I can make a speedy and as well as hopefully accurate prediction for the new atomic environment. So to summarize a bit, so how to construct the machine learning potential, it follows a simple two-step procedure. First, we collect a bunch of relevant atomic environments, and each environment has an atomic energy. The total energy of the system is then expressed the sum of the atomic energy. Now, the machine learning part really comes in comes in when we try to sort of do a sophisticated way of interpolating and have us interpolating between different atomic environments in our that we have collected. Okay, so with that, let's look at with these tools, what kind of predictions are we able to make? So first example I'm going to talk about is about the system of water, which is of course a very ubiquitous system that we are very familiar with. But in fact, there are still many unresolved mysteries about the system of water. So for example, we know liquid water is densest at 4 degrees Celsius, and ice floats on water, which is highly unusual because solid is usually a little bit denser than a liquid. And there's also a very subtle difference between light water, H2O, and heavy water, D2O. The water is also highly polymorphic. It has 20 confirmed ice phases. And amongst the two ambient pressure phases, there's the hexagonal ice and cubic ice. Hexagonal ice is is a little bit more stable than cubic ice. How do we know? Because in nature, all the snowflakes we see are hexagonal, and they are all made of hexagonal ice, but it's left unexplained why hexagonal ice is more stable than the cubic counterpart. So we first train a machine learning potential using the methodology that I described earlier. And here I just want you to make a small mental note about what do we put in our training set. So in our training set, we have about 1,500 bulk liquid water configurations. And I'll come back to this point a little bit later. And before I move on, is another subtlety. So typically we treat electrons as quantum mechanical waves. However, and we usually approximate the nuclei as point-like classical particles. However, for the light nuclei, such as hydrogen, they are very light, and they also behave rather quantum mechanically. And we typically use the so-called the path integral molecular dynamics to account for such nuclear quantum effects. So for example, it's the nuclear quantum effects that contribute to the difference in behavior between H2O and D2O. We know that H2O is the one that we can safely drink, and D2O is quite toxic. So with that, here I'm showing you the density isobar of water. So here I have ice predicted at a classical level, meaning like assuming classical nuclei. This is with the dashed line. So the cubic ice and hexagonal ice have basically same density. And then we have the liquid water, again from the classical simulation. And the solid line is from the quantum mechanical simulation, meaning that we also consider the aforementioned nuclear quantum effects. And then we compare with the experimental measurement. So we can see we are actually rather close to the experimental prediction. And not only we can predict the heat expansion rather well, we also predict the density maxima of liquid water at about 4 degrees Celsius. And we are mostly interested in the chemical potential. We are mostly interested in the thermodynamic property of our system. And to estimate the chemical potential, we use the so-called thermodynamic integration method. And the thermodynamic integration method is really a very general concept, I would say. It reads like even a little bit trivial. So basically we are saying that if there are two systems, and if we can connect them via a reversible thermodynamic path, let's say this path is parameterized by lambda, then the free energy difference between the two systems can be written as just by accumulating the differential difference as we go along this path. It sounds like such a trivial statement, but in practice, because of this flexibility, thermodynamic integration is very powerful. So typically what we do is that we start from a harmonic system. This is because harmonic system has analytic free energy. And then we go we first integrate and towards the classical system. And then the second part is we take another integration by from the classical to the quantum mechanical system with the, you see, the diffuse and wave-like nuclei. And just to a little bit, so here I'm going to show you something that may make you feel a little bit uncomfortable. So so bear in mind that the quantum mechanical calculations are very expensive, and we can only perform such a thermodynamic integration, such free energy estimation using the machine learning potential. However, this is what one would get using two different fits of the machine learning potential. So here are two fits of the neural network potential, and we are computing the chemical potential difference between cubic eyes and hexagonal eyes. And you can see the results are not just quantitatively different, they are qualitatively different. So one is positive and one is negative. Of course, to put things into context, the absolute value here is very small. So that's on the order of 1 milli-electron volts per molecule, but still. So the idea is that we would like to promote our machine learning potential into our ground truth, which is density functional theory in this case, and in order to correct for the residue error. And we not just want to make this correction for a given configuration, but for the whole potential energy surface. So you can imagine like there are two potential energy surfaces, one from density functional theory, other from machine learning potential, and they are subtly different. Now, turns out that if you, so this can be done using so-called the free energy perturbation method. I will not go deeply into the math, but basically, if we write the Gibbs free energy of the two systems described by the DFT and described by the machine learning potential, you can work out the difference. And then here's the estimator to correct for this difference, to correct for the residue error of the machine learning potential when it comes to predicting the free energy. So we add this correction term on top, and you see like now we are getting statistically converged results using two different fits of the machine learning potential. And this is also a cautionary tale because oftentimes people fit a machine learning potential for a given material, and they do not, they treat it as a sort of the ab initio quality, but there will always be a small difference and there will always be a small error. So to summarize the methodology, so apart from the thermodynamic integration part, in the end, we always add a correction term to promote our machine learning results into the true ab initio level. So here's the magnitude of this correction for different systems at different temperature. And you can see it's usually quite small, but it's there. It's also different for different systems. So now we can look at the result. So here I'm showing you the chemical potential difference between cubic eyes and hexagonal eyes. So first we computed at the machine learning potential level, and then we corrected to DFT, and then we also consider nuclear quantum effects. So here the message is that nuclear quantum effects significantly stabilize hexagonal eyes and make hexagonal eyes more stable. So we kind of, so with this, we explain why the snowflakes in nature are always hexagonal. And another example is the melting point and the chemical potential difference between ice and liquid water. So the same idea, we compute the chemical potential difference at the machine learning potential level. We correct it to DFT, and then we add the quantum effects. We can even do this correction term. We can even consider separately the chemical potential for H2O, the light water, and heavy water D2O, and also compare with experiments. So here we are extremely close to the experimental measurement of the melting point. Moreover, we are even able to predict the melting point difference between H2O and heavy water D2O, which is about 4 degree. Now, and some of you may have the question now. So remember that in my training set of the machine learning potential, I only have liquid water, but I was using this machine learning potential to predict the property of ice phases. So how can it be? And moreover, there are actually many phases of ice, and there are 20 experimentally confirmed ones, and there are many, many more that were theoretically predicted hypothetical ice phases. So is our machine learning potential also able to predict the property for these diverse ice phases? So to probe that, we selected 54 phases of ice. So these includes all the experimentally known ice phases, and the other ones, like theoreticians have proposed to be promising ice candidates. Now, if we compare these 54 ice phases with the liquid water configurations that we have. So here I'm just using a simple PCA map. So basically, data points that are close on the map are each point is a ice or liquid water structure, and the points that are close on the map means that the structures are similar, and the points that are far away means that the associated structures are very different. And you can see, so the ones that are annotated are the ice structures, so the ones, the cubic ice and hexagonal ice and so on, and also the numbered hypothetical ice phases. So in general, ice and liquid water are different. And this is not surprising, right? Because they are structurally different and one lacks long-range order. However, the interesting things happens when we instead just compare the local environments, the atomic environments in the ice and the liquid water structures. So the red and the purple dots are the environments from ice phases, and the blue ones are the ones from the liquid water. So you can see that the liquid water environments almost completely covers the ones in ice phases. So what does it mean? It means that if we are learning from liquid water, we are inadvertently already collected and learned from all the environments that are pertinent for the ice phases. And remember that the machine learning potential is basically just based on interpolating between these environments. So this means that the machine learning potential constructed based on liquid water is able to predict all the properties of the ice phases. And we confirm this by computing the density of these ice phases and also compare with ab initio level of theory as well as experimental measurements. And for a number of properties such as density, lattice energy, and also vibrational properties, namely phonon density of states, for the 54, the machine learning potential gives very good prediction. So this is maybe a little bit hard to see, but we can zoom in, and in all these cases for ambient pressure ice, high pressure and low pressure ice phases, the machine learning potential all give very good predictions. And because the machine learning potential is able to predict, perform very nicely for all the ice phases, so we can use the machine learning potential to explore the phase diagram of water. So we computed the chemical potentials for all the 54 and hoping of finding promising experimental candidates. And to our dismay, the phases with low chemical potential all happens to be experimentally observed phases. This, of course, was a little bit disappointing for us, as we were hoping of finding new ice phases. But this, on the other hand, also sort of ascertain the completeness of the experimental ice phase diagram. So we did the same trick. We promoted to a DFT level theory, as well as consider nuclear quantum effects. So here we are. So now we can compute the phase diagram of water based on quantum mechanical level of theory. So in general, once we go to the hybrid DFT functional, we can predict a phase diagram that is very similar to the experimental one. And this quality of the prediction is much better than the phase diagram that were predicted previously using empirical potentials. And another example I want to show you is about a dynamical property. And the reason, so in this case, we want to compute the heat conductivity, which of course is a key parameter in hydrodynamic models and power systems and so on. Now, the traditional way of computing the heat conductivity is the so-called the Green-Kubo relationship. Now, in this Green-Kubo relationship is based on taking the integrating the autocorrelation function of the heat flux. This is actually quite problematic because you see this integral goes from 0 to infinity. But because of the numerical noise of the autocorrelation function, if you indeed integrate to infinity, this integral is divergent. So there's some numerical issues there. But apart from that, there's also a very severe conceptual difficulty. So the heat flux is, the reason is like the heat flux is actually ill-defined. The reason is that if you look at the expression for the heat flux, it has two components. The first one is based on the atomic energy, and the second one is based on the pairwise forces between two atoms. And because the interactions in our atomic interactions in a material system is always many-bodied and long range. So and also, of course, it's non-local as well. So there's no unique way, and there's also no obvious way of finding the atomic energy as well as pairwise forces. And indeed, remember that the machine learning potential was constructed based on this atomic energy, but this is more like a mathematical device instead of a sort of a physical quantity. So for example, if you compare the atomic energies from, again, this 2/5 of the machine learning potential, this is again for water, it's not correlated at all. And even when you look at the molecular energies, so this is for water. If you look at the energy for each water molecule, again, there's almost no correlation. However, we managed to find a way that bypass this Green-Kubo relationship, but instead just based on our calculation on the density waves. So how does it work? So in our atomistic system, we have a particle density field, and which is purely based on the position of all the atoms, and it's a very well-defined quantity. So it turns out if you take a Fourier expansion of the particle density field in space and time, what you will end up with is that the autocorrelation function of this particle density field for each wave vector in space K can be have two decaying modes. One is exponential decay mode that is related to the heat propagation, and the second mode has an oscillation and is related to the sound propagation. So which means that we can compute this autocorrelation function of the density wave and then fit it to the hydrodynamic equation in order to obtain the heat conductivity. So this is what we did. So you can see the dashed line or the solid line. So one of them is the simulation data, the autocorrelation function, and the other is from the fit, and they are hardly distinguishable. And from that, we are able to compute this lambda, which is the heat conductivity at a different wave vector. And one can then extrapolate to k equal to 0, which then give us the macroscopic heat conductivity that we were after. So with that, I would like to conclude. So I hope I have convinced you that machine learning potential is a powerful tool to bridge the gap between quantum mechanical calculations and macroscopic properties. And however, there's also a lot of open questions on how to best construct and utilize machine learning potentials. And we are also excited to see what can we do next. Thank you so much, and I welcome any questions.
Thank you, Bingqing. Very, very interesting. I'm gonna take questions from the audience now, if that's okay. So if you have any questions, you can unmute yourself or raise your hand or type on the chat, and I'll read them out loud for you. Siva?
Yeah, thank you, Bingqing, for the very nice talk. There's a very interesting point I've observed in your talk is you said when you making your training data set with the water, and actually you can predict the property for the ice phase. So I was wondering, is these some points that is generalizable for other different type of materials, or it's more like something specific, because then you have explained that you have checked the properties that actually the water can cover the properties of the ice in the in the future space probably. So my question is, do you think, have you observed these with other type of materials, or do you think it's more like a specific case?
So I think it's something in the middle. So for water, it works particularly well, and for other systems that are quite similar to water. So for example, if you have a carbon and silicon, and these things also have a very similar network structure, that also works really well. And we also know the systems that this doesn't work at all. So for example, if you have hydrogen solid, high pressure hydrogen, the solid is molecular and the liquid is atomic. So they are completely dissimilar. Now, in practice, one can check very easily just by making this type of sort of similarity maps. So if it's indeed like this sort of coverage as we see, then I think there's a good chance that one can do some extrapolation using the machine learning potential from the liquid to the solid phases.
Okay, thank you. But so when you plotted, then how you made the choice of your projections is like the physical properties that you used in your regression problems, right? For example, if the picture is here, how you decide when you project that point to the space. It's just when you said to compare the similarity, I was wondering how that is computed. So you need to take the features that you used as the input and to check if the relations are similar.
Right. So this is unsupervised, right? So this is completely based on the features.
Okay, thank you. Thanks.
Any other questions for Bingqing? At the end, sorry, I have two questions. I forgot the number of the slide, but you were mentioning, can you go back a bit? I'll tell you where to.
Going back.
Yeah, you go one forward. More, it was like a neural network with a name of two guys. Oh no, you passed it. No, keep going forward. That one. Sorry, I just got a bit lost. What was the difference of the Beller-Parinello neural network, and why do you choose to use that one for this?
Well, so they are at the moment there are a few different schemes on the market, like there are a few differences between them. So, for example, how do you featureize your atomic environment? So the Baylor-Parinello neural network, they use the so-called Baylor-Parinello symmetry functions. And if you use the slope descriptors, that also gives you another implementation of the machine learning potential. And recently, there's also this message passing, basically sort of graph-based neural network. And then how do you do this the interpolation? Right. This also gives you different algorithms. So people can use machine learning, the neural network. There are also people use Gaussian processes, and there are also people just use linear regression. These are all like valid choices. Now, which one is better is actually a very difficult question, because as far as I know, no systematic benchmarks have been done.
Oh, I see. So it's quite difficult to like benchmark which one is the best.
Right, because the difficulty, there are many difficulties. So first of all, fitting these things is not completely trivial, right? And it's hard to find someone with all the expertise of different implementations. And then secondly, like typically when we compare machine learning models, we just compare the error, right? The RNFC of the test set. Now for machine learning potential, because I'm using the potential to simulate a system. So it's not just the accuracy not just the RMFE on the test set that matters. I also care about the stability of the potential and so on, and also how well it extrapolates. So it's also very difficult to judge.
Yeah, I see. Okay. And when you mention message passing, so that's used on geometric deep learning. Do you think that's kind of like the way forward, or what do you think about it?
Right. So the latest the latest one, like as the is the equivariant message passing one. It's hard to say. I do think it has a lot of promise, but on the other hand, the performance on a benchmark. So if we just look at the prediction of the energy of small molecules and other benchmark data sets, not talking about the machine learning potentials. So that scheme is on par with sort of kernel machine-based methods.
All right. Yeah, thank you. Yeah, last week we had Max Welling. He was talking about the equivariant message passing. Yep, that's from me. Anyone else has any other question? Chendan?
Yeah, so my question would be, so you've mentioned to when Sibyl asked the question that you know that this will work well for some things like water, like silicon, and all of these. Oh, and by the way, it was a very nice talk. It was the first time since my high school years that I heard again about the Gibbs free energy. So I wanted to ask, so for all these, let's say, various different liquids that this kind of method will not work well with, do you have any ideas or plans about how to, let's say, understand these liquids better?
Sorry, so let me try to understand your question a little bit more. So are you asking like how shall we interpret like liquids that has these solid-like fragments or like the other way around?
No, so basically you've said to Sibyl that there are some, that this one will work well for water, but not for all of the materials. So for the, let's say, the other materials that you don't know that it will not work well with, what are your plans or what are your thoughts about how to, let's say, understand these materials better?
Right. So I actually so there are two aspects. So first of all, I think it's a very peculiar thing that for water and silicon and all that, and maybe some other sort of glassy like materials that works well. And I think that's very peculiar, and I view them as outlier. And for me, that seems to me suggest like liquid water. It's like small pieces of ice, like piecing together.
Yep.
And that says something about the strangeness of water and also some other glassy liquids. And I think in general, there's no physical reason why this liquid to solid extrapolation should work well, right, for many systems. Now, on the other hand, so from a practical point of view, when we are studying a sort of a general system, there are still quite a lot of advantage from learning from the liquid, because the liquid configurations are, because the liquid has a very large variety of different environments, because in a solid, it's always the number of different environments are very restricted. So when you are doing learning, you kind of want to have a diverse training set. And that's where the liquid offers an advantage. And for many materials, learning just from the liquid is probably not enough. So one can probably attempt, okay, having a liquid as a sort of a base training set, but also adding solid configurations.
Yep. And so basically you collate all of these training sets, not only from liquid, but also from solid configurations. And
Right.
using these training sets, you can do interpolations between the various environments that you already have. Based on these interpolations, you can predict, let's say, what would be the state that the, let's say, the particle or the thing will be in, right?
Mm-hmm.
Yep. Okay. All right. Thanks.
Okay.
Thank you. Any other questions? If there's no more questions, we can leave it up to here and we can say thank you to Bingqing. Bingqing, thank you so much for doing
Thank you so
this
much.
talk. And yep, that's all. Thank you everyone for attending today. And
Thank you. Have a nice day.
you too.
Thank you, Bingqing. Thank you, everyone.
Bye.